So please join me in welcoming Dr. Jason Patton.
Check, check. Well, thanks for having me. And in a moment, I guess with further ado, and a little bit more ado. Okay, so sea level rise along coastal Northern California, how tectonics influences sea level rise, with cameo appearances from Todd Williams, Jeffrey Anderson, Tom Leroy, Reed Burgett, Mark Hempel-Haley, Bob McPherson, Ray Weldon, and Kyle Weiss, large team of scientists who have contributed to the content of this presentation. Oh, and there's lots of material here, so please contact me and I can provide you with all the slides. And this is a paper that just came out that summarizes. Let's see here. Okay, so there are three types of plate boundaries. There are divergent plate boundaries, where plates move away from each other. There are convergent plate boundaries, where the plates move towards each other. And there are transform or strike-slip plate boundaries that move side by side, like the San Andreas Fault. And I'm going to use the controller now. Oh, yeah, I am using the controller now. So, in this video, this is along the East Africa Rift, a divergent plate boundary, and this is a lava lake where the lava cools and forms a crust. And if we watch this long enough, we can actually see all the different types of plate boundaries. And there's a YouTube link in the presentation. So let's take a look at the Cascadia Subduction Zone, a convergent plate boundary, aka the CSZ. And here on the left, we have a map of British Columbia, Washington, Oregon, and California. And we can see where the Gorda, Juan de Fuca, and Explorer plates are subducting along the Cascadia Subduction Zone fault beneath the North America plate. And here's a cross-section showing the oceanic plates subducting beneath the continental crust, continental plates. And let's see here. So between earthquakes, the fault is stuck like Velcro, and the North America continental plate is pulled down like a rubber flip-flop. And that's where the island with the tree is subsiding when it's being pulled down. And when the stress is greater than the strength of the fault, like the Velcro, the fault slips and we get an earthquake. So between earthquakes, the interseismic period, part of the crust is pulled down. And then during earthquakes, that part of the crust that was pulled down gets pushed up. And that's what lifts the seawater column up. And then the water has gravitational potential and it falls down, and then it oscillates up and down, and that's what generates the energy for tsunami waves. And and here's another diagram that sort of shows the earthquake cycle. It's from Brian Atwater, and I included just to help us learn about the word interseismic and coseismic, which mean between earthquakes, inter-earthquakes, and during earthquakes, like you're cooperating with the seismic. And right now, we are in the interseismic part of the earthquake cycle in Cascadia. So here's a real world, some real world data of during earthquake vertical land motion from subduction zone earthquakes. So here's up in Alaska, here's Anchorage, and in 1964 there was a subduction zone earthquake, and this area in red, highlighted in red, went up during the earthquake, and this area in blue went down during the earthquake. And this is a profile going perpendicular to the fault, showing the area that went up and also the area that went down during the Good Friday earthquake in 1964. And also we could see the same thing happened in Chile in 1960, magnitude 9.5 earthquake. And it also happened in 1946 along Japan, the Nankai earthquake. And the vertical axis here is either coseismic up and down or interseismic up and down. And I've highlighted in green observations of coseismic up and down. And we can invert that. So now we have the light green coseismic deformation. And if we highlight what the interseismic motion was, it looks a lot like the coseismic. So that's sort of showing us how the crust is elastic and the opposite things happen during the earthquake. So how do we know this has happened in Cascadia in the past? So imagine you're a happy tree and you're living just above high tide, near, like maybe near the bay or something like that. And, part of the crust is going up in between earthquakes, and then it goes down during earthquakes. So let's say you're in that part of the subduction zone, and during the earthquake, the ground goes down, and then the tide inundates your roots, and you die. You're no longer a happy tree, and then the sediment fills in, and the earth crust goes up, and then you have plants growing again. So we have evidence of this all up and down the coast. This is a map from about almost 20 years ago, and each of those white circles is one of these locations where we found evidence for co-seismic subsidence. Oh yeah, just keep trying to use that. Here's a photo from the coast along Willapa Bay in central Washington. And if you're up here like I am, you can see that there's seaweed and barnacles growing on these trees. Do barnacles grow on trees usually? Not living trees. No. Thank you. And so these trees were happy before the last Cascadia subduction zone earthquake, before the ground subsided, and now they're below sea level, and we have seaweed and barnacles. Here's a photo I took in 2014 at the Seismological Society of America meeting up east of Anchorage. And here's a tree that was happy before the earthquake, the Good Friday earthquake. And you can see that it's rooted in this nice dark brown soil. And then the earthquake happened, it subsided, and has since filled up with lighter gray mud. And eventually it got high enough so that we get vegetation growing again. So here's a photo that my colleague Sataki-san took after the 2011 Tohoku Oki subduction zone earthquake and tsunami in Japan, East Japan. And these are areas here that are flooded now that were above high tide before the earthquake. So the area subsided and now they're flooded. And I like this photo because it reminds me of the geography, the local geography. And it might be how it might look like here after the next subduction zone earthquake, or not, and we can talk about that later. So if there's a tsunami and there's a source of sand, that tsunami might transport that sand and deposit it directly overlying that buried soil. And again, we have a map showing where those tsunami deposits have been found. And all along the coast, including Humboldt Bay. So that's what my master's thesis research was about, was looking at co-seismic subsidence along Hookton Slough, and we found evidence for tsunami. So in this core, that if you were up here you could see more clearly, there's this nice brown soil that's overlain, marsh deposit, overlain by pebbly sand, and then sandy mud, and then overlain again by mud. So we've got tsunami here too. And so Brian Atwater, who actually published the first paper about using the sediments to infer earthquakes in 1987, before that we were still debating whether or not earthquakes happen in Cascadia. He compiled all evidence along Cascadia, and here's an outcrop in central Washington, and each of those horizontal lines represents a buried soil, and he put this all together in a USGS paper that anyone can download for free. You just do a little internet search of the orphan tsunami, and you can learn more about that. And I'm going to go quickly through some of these slides. So we also have evidence for ground shaking generating submarine landslides that go downslope and turn into turbidity currents. And so we also have an earthquake record offshore. And this is a map of the subduction zone showing these different regions. And it looks like that the subduction zone ruptures in different segments at different times. And so these different areas have different return periods. So these are the average time between subduction zone earthquakes for each of those areas. And you can see in southern Oregon, northern California, the average time between earthquakes is about 220 years. So what does this have to do with sea level rise? Like, hey, I didn't know I was going to learn about earthquakes. So here we have the Humboldt Bay Vertical Reference System Working Group, HumBayVert, that Todd Williams put together in 2010. And I'll talk about the work that we did to look at sea level rise and tectonics. So here's some plots that my colleague Jeff Anderson put together for Crescent City and the North Spit. And this was sort of the beginning of what the problem, Houston, we have a problem, right? So in Crescent City, you can see over time, from 1933 till recently, the elevation of the water surface as observed in the tide gauges, and this is, let's see, this is monthly, and this is a summer average monthly mean sea level, which takes out some of the noise from storms and that kind of thing. And you can basically see that the trend is downward. So Crescent City sea level is going down, and in the North Spit, which has a shorter record, sea level's rising. So Crescent City about 1 millimeter a year down. North Spit almost about 4 millimeters or so a year sea level rise, and that's more than what the Northeast Pacific sea level rise rate is. So what's going on? What's going on in Crescent City, and why is sea level rise falling there? So basically, if sea level is falling, that means that the land is rising faster than sea level. And if sea level is rising faster than regional sea level, that means the land is subsiding. So basically, the crest in Crescent City tide gauge is experiencing tectonic uplift, and the crest at the North Spit tide gauge is tectonically subsiding, plus maybe some other stuff. So Todd put together our group of over 30 state, local, and state, local, federal agencies, academics, and organizations, and individuals. And we all met, and we gave presentations to each other. And here's the sign-in sheet. And we discussed what the problem was. And so basically, the issue is how does land subsidence control sea level? And we identified how accurate measurements of local land elevations in the Humboldt Bay area are important, and this is a priority issue identified by Army Corps of Engineers, the Coastal Commission, NOAA, National Geodetic Survey, and others. So it's important. Someone's got to do something about it. So we, as part of the HumBayVert and Cascadia Geosciences, sought some funding to use tide gauges, benchmark leveling, and GNSS observations, used to be called GPS, to look at the ground deformation. And we got some money from the U.S. Fish and Wildlife Service after a couple workshops. And here's sort of like a summary of the science and the problem. So we have sea level change based on glacial, interglacial cycles and anthropogenic forcing. We've got tectonic deformation. Just want to mention what local sea level is. Local sea level is a combination of the regional sea level and land level change and whatever other factors you're going to be considering. In our solution to look at this is to apply this geodetic methods, and we use tide gauges, benchmarks, and GNSS observations. So this is a sea level plot, relative sea level plot at Huon Peninsula in Papua New Guinea for the last 140,000 years, and it's basically the glacial interglacial cycle. So 22,000 years ago, the last glacial maximum, lots of water was trapped in the glaciers, continental glaciers, and when those started melting, and so sea level rose because of the melting ice and thermal expansion and some other factors. So that's the long-term, sort of like background natural cycles. Remember, we are in the interseismic part of the earthquake cycle. And then I have a couple plots just showing some previous estimates of vertical land motion rates. And so this is from Paul Vincent's work, And don't be a lazy student and publish your work if you want to publish it, or your advisor will have their next student publish it in their name and not yours. So that's this lesson. So 1994. And so in the gray area is the area that's going down, and this white area is the area that's going up. It's nice and heterogeneous, like you might expect it to be. Then Paul Fluke in 97 generated a model. You know, this area is going down, this area is going up. And Cal and Wong did another one. This is just coseismic subsidence contours that you could see if you were up here. And he compared it to these paleoseismic studies. Well, something else that we identified that Houston was a problem is that, so these are plots. They're basically the same data. So we go east to west from Reading to Arcata, and this is the uplift rate. And in these previous papers, they showed that as Arcata. Excuse me. And it shows Arcata is going up at, between a little more than 3 to a little less than 5 millimeters a year. So we looked at the longitude, and that's actually Burnt Ranch. And we contacted these people, and they didn't recognize that. So that's another thing that we're contributing to. One other thing that happens is as the ice melts and goes out into the oceans, there's less mass over where the glaciers were, and then there's more mass where the oceans are because there's more water there. So the crust around where the glaciers were goes up, and the crust where the ocean is goes down, and then there's also some horizontal motion of the mantle as it redistributes. So that's called a glacial isostatic adjustment, and this is a map that just shows how we have models that show, whether it's going up and where it's going down, and so we subtracted that out of our analysis so we could focus just on the tectonics. So geodesy is the science of accurately measuring and understanding Earth's geometric shape. So we sought geodetic data to evaluate plate tectonic deformation as it contributes to spatial variation in sea level rise rates. Now you're all geodetic experts, all right? Just like you know what to do during an earthquake, right? Drop, cover, and hold on. So now you're emergency management experts. You know what to do. You're an expert. Okay, so what are our methods? Tide gauge data. So we acquire and analyze existing data. We deployed some tide gauges to some historic locations, and we subtracted eustatic or regional sea level rise from those site data to come up with the rates of sea level at those tide gauges. Benchmark level data, so there are benchmarks all along the highways that have been surveyed with high precision, first order precision leveling surveys. And so we used survey data from between 1967 and 1988. And then GNSS, those are, give you positions, high precision positions, say that 10 times. And those are basically about 20 years worth of data. And as I mentioned, the Crescent City tide gauge goes back to 1933, but all the other locations like North Spit and Mad River Slough, all those other tide gauge locations only go back to about 1977, 1978. So some of these data overlap and some don't. All right, so once again, here we have the subduction zone and zoomed in. Let's see, I think I clicked. Whoops, no, I don't click. So zoomed in to where we are, Humboldt and Del Norte counties, Crescent City, Eureka, Mad River Brewery. It's right there. I should have put that on the map. This map shows white dots, white circles where we have geodetic data, and I also put these black lines in here, and these are all of the active faults, quaternary active faults, so faults that have been active since the last 2.56 million years, just to show, where our observations are. And okay, I got time. And if we zoom in, we'll get to. Okay, great. So we can zoom in just to see here around Humboldt Bay. The triangles are the benchmark sites. The white circles with the dots in them, those are the GNSS observations. And these gray circles with the crosshairs in them are all the different tide gauge locations. So Jeff Anderson operated the campaign tide gauges and did our analysis for the tide gauge data. Reed Burgett, he did the analysis for the benchmark leveling data. And then Todd Williams and myself basically downloaded the GNSS data. So, yeah, heavy lifting. Okay. So, speaking of heavy lifting, this is heavy plotting. So, let's see here. I like to read this. So, the tide gauge results showing sea level rise rates. So, on the left are the tide gauge data. Solid black lines are linear regression fits, and the dashed blue lines are weighted least squares regression rates, so which are, almost exactly the same. And the table on the right represents the rates calculated with these data. On the right, these are plots that show how each tide gauge is moving relative to Crescent City. Excuse me. Because we had to. Because Crescent City has the tide gauge record that's actually long enough that you can analyze, so we difference everything and compare everything to Crescent City. Something to note is that here, again, we can see the sea level is falling in Crescent City, and then if we look at the slope of these sea level rise rates, we see that they are getting steeper to the south. So Hookton Slough has the highest rate of sea level rise. And then this is a really big table, but we're going to zoom in to, let's see, one more click. Oh, no. Okay, so, check. All right, so our tide gauges from north to south, and these numbers here. Check. Awesome. I think it's this. So these are the local sea level rise rates for these different sites. And so Crescent City, we came up with, close to what, without our, doing the filtering that Jeff did, about minus 1 millimeter a year. And Hookton Slough is experiencing sea level rise rate of about 6.5 millimeters a year. So much more than the regional sea level rise rate. And this is a map that shows the vertical land motion rates. So red is going down and blue is going up and yellow is sort of in the middle. And so we can see that around Humboldt Bay is going down a lot compared to the rest of the area. And this is a table. I wonder if okay. Let's see here. Okay, here, yeah, we can see, it's just a little bit more visual. If we zoom in to Humboldt Bay, we can see how much more red these symbols here in southern Humboldt Bay are than they are relative to northern Humboldt Bay. So the vertical land motion in Hookton Slough, so without the glacial isostatic contribution, is about 6 millimeters a year. So it's really going down in Hookton Slough quite a bit. And now let's look at these plots. So the upper plot, now the vertical axis on both of these plots is vertical land motion rates per millimeter per year. So let's see here. So this is, let's see here. So this is 0, -1, -3, -5, -7 millimeters per year. So these are 2 millimeter a year increments. And the top plot is basically west to east, and the bottom plot is south to north. So the top plot is like if you're in Willow Creek looking to the west, and the bottom plot, you're in Garberville looking north, and this is like if you're Willow Creek looking west. So if we're looking north, we can see that these two regions here, these are geodetic locations around Humboldt Bay, and these are geodetic sites in the Eel River Valley, the lower Eel River Valley. And we can see that both of those are going down, and there's a westward downtrend. Remember the subduction zone? So we think that this is indicative of the subduction zone pulling down the crust like that. And then if we, if we're in Willow Creek looking to the west, we can see I've highlighted the Eel River Valley, Lower Eel River Valley, and Humboldt Bay regions again, and we can see that it's also being pulled down. And something else that was interesting is that when some of these, and we'll look a little bit more closely because you won't be able to see what I'm trying to show here, but as in some places there were discrete offsets in vertical land motion rate, and that's right where we crossed a fault. So we actually, it looks like that we have evidence of the fault having different vertical land motion rates on either side of the fault, and so we'll take a look at that a little bit too. And one sort of last slide on vertical land motion. So north isn't always up. Don't let anyone fool you. North isn't always up. So here we have Humboldt Bay. This is Arcata, Humboldt Bay, South Bay, the Eel River Valley, and this is Table Bluff right here. So these are, apologies, this is an older figure before I went to AFN, color blindedness colors. So so if you're red, green blind, I apologize. But the red is going down and the green is going up. I just haven't updated this figure yet. So, so the triangles here are our geodetic data, and the color on the map is actually, it's INSAR, I-N-S-A-R, which stands for Interferometric Synthetic Aperture Radar, which basically, big words, but you're going to learn what it is, and then you're, an INSAR expert. So basically, they take radar data at two different times and look at the wiggles from the radar data and difference them to find out the rates of motion. So this is actually a map showing vertical land motion using radar data, and so it's fantastic because it gives us an estimate of the vertical land motion rates not near where our geodetic sites are. Of course, there are lots of things that contribute to vertical land motion, including groundwater pumping, lots of things, the seasonal hydrological cycle. But the cool thing about this, because everyone asks me, oh look, here's North Spit, tide gauge and benchmark data. It's like it's going down out there. Well, duh, it's mud. It's sitting on mud, so that mud's compacting. So what this is really cool is it shows that both Table Bluff and the Eel River Valley are both subsiding. So it suggests that geology isn't the first order, sediment or material that your geodetic site is embedded in doesn't appear to be a first order control on vertical land motion rates. And just a couple more slides. So I wanted to link our geodetic study with using LiDAR data, because I think the next talk is going to talk about some LiDAR data. No? Okay. Well, I'll still do it. Okay, because LiDAR data are cool and they're free and you can download it.
Let's talk about LiDAR, Jay.
All right, I'll talk about LiDAR. Yeah. Okay. So again, here's a map showing the crustal faults and check. Yeah, I know it's me. Check. Yes. Okay. And we're going to be looking at some data associated with this rust fault that's highlighted in red now. So we're zooming in, and this is the Lower Eel River Valley, and these are our geodetic sites. Again, I'm sorry, this is an older map, so red is down and green is up. And the white lines are all these different crustal faults. The Little Salmon Fault, one of the most active crustal faults here, is in red, and then this is the rust fault in white. And we're going to look at the geodetic data as they cross these two fault systems. And eventually we're going to end up in Shively. So we'll zoom in to this plot. And so this is, south is to the left, north is to the right. These are 1 millimeter lines of vertical land motion rate. And the yellow circles, oh, it's backwards. The blue circles are on sites that are on the south side of the fault. Yellow circles are on geodetic sites on the north side of the fault. And there's basically difference in 2 millimeters a year across the fault. So we think that we've identified that the fault is having some sort of influence on these geodetic sites. So that was pretty exciting. And then when we went and we identified 7 places where this happened. 5 of them are active, known active faults. This is one of the places that's across an active fault, but it's weird. So again, the yellow ones are on the north, the blue ones are on the south in general, and there is an offset of about 1 millimeter a year between these sites. So here, this shows that the north side is going up about 1 millimeter, almost 2 millimeters a year more than the south side. Now, this was a problem because the rust fault, which is what fault this crosses, the rust fault is actually up on the south. So this is the opposite what we would have expected. All right, so Houston, so Tom, Leroy, and I started looking at the DM data, and at that point, there was only 10 meter resolution DM data, and we actually thought we found it. So that night, I discovered that Bill Dietrich had actually flown LiDAR a couple years before for the Eel River Critical Zone Observatory out of Berkeley, and I downloaded the data that night, I mosaicked it and hill shaded it overnight, and I woke up in the morning, and I found that in Shively, we had this beautiful topographic scarp right where we thought it was on the 10 meter DM, which is really neat, and we can zoom in a little bit. So this is Shively Creek, and we could see this shaded relief. So this is a shadow, an artificial shadow, showing that this side of the river terrace is higher than this side of the river terrace. And basically, so here's a photo from the road right by the railroad in Shively, and we can see that this building and that building are built on the same terrace tread, and it's been uplifted on that side. And so basically, there's a fault at depth that's uplifting one side over the other, so we can make some measurements about the size of the scarp. And if we know how old the terrace is, we can come up with a slip rate for the fault. So I've done a whole bunch of measurements and made estimates of the terrace age, and I've come up with a slip rate, bracketed slip rate range of between 2 and 3 millimeters a year. And that's exciting. And so here we're going back, to the last slide. If anyone has any questions, we can wait till at the end. Okay, great. Thank you.